And where you have the minimal value, the lowest value, that is the weaker side. So you need to be careful on that side. So that is referred as controlling section modulus. So we'll do this. Then the bending stress at point H. So you need to figure out that what is the stress at this point. Is it compressive or tension? The maximum bending stress. Then you need to figure out that where the maximum stress is happening on the cross section. Again, depending on if you have the largest distance towards the lower bottom side or the upper side, based on this thing, you will decide that which fiber is in the highest or is experiencing the maximum bending stress. So this is pretty much similar what we have done last time, only this is just flipped one. So students, do you remember what were the steps we did last time? What were the different steps we did? How can we calculate the centroid? What's the very first step? Yes, anyone?
Find the total area.
Find the total area, but there was one more thing that is required before we do anything. Establish reference, right? So the reference is generally ground here. So we'll establish reference axis. And then we look into this composite structure into the possible number of areas, right? So for example, this is one area, let's say, one rectangle, I call this area 1. And then I have this second rectangle, I call this area 2. Okay. Now, what I need to do is I need to develop this equality. I need to say that if I'm talking about area 1, rectangle 1, then centroid into area, I can write it like this for area 1 plus centroid for area 2 and area 2. If I take this like a product of centroid and area for the individual areas, then it should be equal to the total area, right? Where I can add both of the areas, the total area and the common centroid. So I'm just calling it y. So y dash can be written or yt if you want. So this left hand side should be equal to the right hand side. Here I am taking the individual areas and here I'm writing it together. Like AT is the total area where A1 plus A2 is mentioned, right? So this equality should hold. So if I rewrite, if I want to know that what is the overall centroid, I can separate it and I can take this AT on the other side. AT is nothing, AT is just A1 plus A2, the total area, right? So I can take this AT on the other side like this. So this is the formula that I need to evaluate, right? I'm solving it basically. I'm plugging the values, and once I do the calculation, I will figure out the overall centroid, which is the total centroid. You can say that location for this composite structure. So what book or what this text is referring, it's telling you that, for example, you can make this table to facilitate the calculation. So for example, this is the area 2, right? In my nomenclature, I call this area 2. This is area 1. The technical names are referred as top flange for this part. This is top flange, and this vertical beam or portion of the beam is referred as stem. What is the area of A2? What is A2? What should I write? Area of rectangle 2, what is it?
You just multiply 125.
Yes. So you just simple write it's 25 into 100 and it is 2500. You can see this is the area. Similarly, when I want to calculate area for the first one, then it would be 150 times 25. So once you do the calculation, it would be 37 50, right? 3,750. By the way, we need the total area as well in the formula. So I can add them and I can figure out this is the total AT. This is the total area as well, right? So I know the individual areas and I know the total area as well. Okay, then I need to figure out first the individual, where are the individual centroid? So students, where are the individual centroid for the first area, let's say? If there is a rectangle, which is like this, where would be the individual centroid?
150 divided by 2.
That's true. So it would be somewhere here, right? And it is the half of the vertical distance. The total distance is 150. So this should be at 75 or 150 divided by 2. This is 75, right? So you can see this 75 is the centroid for the first area. And what about the second one? Second one is in the middle of the top rectangle. But here, because our reference is from here, so this total distance needs to be taken into account, which is, how much is it?
162.5.
162.5, where you are adding 150 plus 25 divided by 2, half of 25, right? Which is 12.5, I believe. So 150 plus 12.5 is 162.5. Okay. Then if you see here just we are adding, we are doing the product. So that you know that I need to take product individual for individual areas. So if I multiply these two, I will get this product for area 2 and I will get this product for area 1. So you can say that area 2, this will come here. Area 1, this will come here. And I already know the total area that will come here. So the only unknown is this, right? Sum of individual area and product of area into into the centroid divided by the total area should give me the total centroid. So when I perform and I plug all the values, you will see that I am able to get 110 mm, which means that the overall centroid for this structure will be at the value of 110 from the reference level. So this is 110 from the reference, and this is the overall centroid, the complete centroid, the total centroid. Okay. So students, this makes sense. This calculation is fine. Any question related to this? If you have questions, please go ahead. Should we move forward? It's fine.
Yeah.
Okay. So this is the first part where we figure out the centroid. Now we need to calculate the moment of inertia. So do you remember what was the formula of moment of inertia for a rectangle? We used it last time. How do we calculate I for a rectangular cross section where the width is B and the height is H?
BH
1
cube
over
divide
12.
12.
1 over 12,
Oh.
yes. So it is 1 over 12 BH cube. And if you go to my previous slides, I have shown you this as well, that technically this is coming from the integration. You first assume a small strip of area like this, and then when you plug limits in it, then it will come up as 1 over 12 BH cube based on the limit. So anyway, this is the formula for the rectangular cross section. How many rectangles we have? We have, this is the first rectangle. And this is the second rectangle, right? So students, now I need to know what would be the moment of inertia. I call this A1 for the first rectangle, and what is the moment of inertia I2 for the second rectangle. Can you do the calculation? Can you tell me the value? So we'll check in the next slide that our values match or no. One over 12. What is B in the first case?
25.
25 into 150 cube. And here again, it's the 1 over 12. 100 into.
Professor,
Yes.
for the first one, I got the answer,
Okay.
which is 703
703.
1250.
1250. And this is the units are millimeters. So you have 4. This is raised to power 3, millimeter raised to power 3. This is a separate one. So m raised to power 4. These are the units. Okay. And what about the second one? Second moment of inertia or second area? What's the value for the second one?
It's 130
130
208.3.
208.3. Okay. Okay. So we'll check these values, but before we move, students, how can we transfer? So what I calculated now, what I have calculated, for example, I1, this I1 is valid only for the first area and the centroid for the first area. This I2 is valid only for the second rectangle and the centroid location. I told you that when you want to shift this I here, you use parallel axis theorem. So what you need that what is this common distance between the two centroids that you want to transfer. Area you already know. You already know this area. If I shade this, you know what is area 2. So if I want to shift this I2 with respect to the main centroid, the overall centroid, because this is the idea. You first calculate the individual moment of inertia, and then using the parallel axis theorem, you shift all of these these individual moment of inertia for the final centroid, for the total centroid. So the parallel axis theorem says, let's say I call this I total, that is for the total centroid. So you need to put I2 plus AD square, right? Where D is nothing, it's just the distance between the two centroids, the current centroid of the individual area with respect to the total centroid. So can you tell me if in this case, what is this value? What is the value of D for the upper rectangle, top flange? What should be the value of D? Where was the total centroid located? 110, right? We calculated it's 110. Yes.
Is it 52.5?
52.5. So total is 175 minus 110. It would be how much? It would be 65, right? And 65 minus 12.5. So this is around 52.5. Yes, that's true. 52.5. So when I convert this thing, I will write the value of I2, which is 130,208 plus what is the area of that rectangle? Area is 100 into 25, right? And what is the D value? It is the 52.5. square. Can you quickly do the calculation and tell me what's the total centroid when you use I2? What's the total value? Yes,
It
students.
says 7020
7020
833.
833. Okay. And can we do the same for I1 for the first one? Because we need to transfer this one as well. It's currently present somewhere here, half of the height, 75. We need to shift it from here to here. So you need to do the same thing for I1. What should be the value of D in this case?
0.
No.
For which one, Father?
For the first rectangle, the centroid I1 is calculated with respect to the half of 150, which is 75. Our centroid, total centroid is higher, 110. So we are
35.
technically talking about this. This is 110 minus 75, so this should be 35. Students, can you give me the value for this total, the second part, this one, with respect to I1?
It's 529
It's 529
6875.
6875. Okay. And then because you need to merge these two, so you generally add this one and this one. If you have three areas, rectangle areas, then you will add all three to figure out the total actual value of I. So I'm calling it IT1, IT2. So I will just add this IT1, right? That got transferred from the first area, and this is the second that got transferred from the second area, and this is the actual one that I will use when I'm going to evaluate this formula. In fact, I'm not C, I'm Y over I. Right? So this I is the one that will be utilized in the formula for calculation. So we have the values. Now we'll quickly check if we are going to see this thing. So I can see that. So for the top flange, we got this thing, right? 103. This is the one we got. For the other one, we got 7031,250. So this is also here. Value of D is also correct for us, right? Students, did you, this is also correct.
So I2
This is
is not
correct.
correct, Professor. I think I forgot a number.
You didn't use square?
No, I used it, but I forgot the 0 in the IC.
Okay, okay.
So it
So,
will be the one written.
so
The
it is
11.
this one, 11,625,
Yeah.
right?
Yeah.
Okay, so when you do the calculation for this one, it will be this number value. Okay, should I erase students the writing so you can see the table clearly?
Yes, Professor.
So you add this thing, this is the value of I that is required in order to solve the formula or to process further, you can say that. So students, I have told you that what is section modulus? I will write again. Section modulus is basically if you rewrite the formula and instead of writing y with respect to m, you just mention it like this ratio. This is called section modulus, right? And generally, this value differs based on you're looking for the upper area, you're looking at the lower area, for example. So this value will fluctuate, right? And the lower value is showing that this is the weaker side. The lower value is the weaker one, right? Where it can easily bend, for example, or where it is weak. So this is, we call it a controlling section modulus. So if I show you uh, the, let's say here, so this is the centroid here. This is its present. So I need to do one calculation for this extreme fiber for the section modulus, and I need to do one calculation for this upper fiber, the top flange and the lower fiber, the outermost fibers, you can say that, right? So what is the value of y here? This is the value of y, right? If I'm talking about the first case, the outermost fiber on the top flange. So what should be this y when I do the calculation? Yes, students.
65.
So total is 175 minus this is located at 110, right? So it should be 65. And this should be a positive y in this case, right? Here in the section modulus, it will not make much sense, but definitely in the calculations for stress, it will be. So I will just show you. If you see for the top flange, this 175 minus 110, this will give you 65. Value of I you have already calculated. Once you calculate and add the total value, now from this point onward, you will be using this. This is that will use in all of the calculations. So once you solve this ratio, you will get one number here like this, right? And students, what about the other side, other fiber? So it's like this, right? It's here. The total centroid is somewhere here at 110. We know that for the outer one, this was 65. But what about the bottom one, outermost fiber on the bottom side? It is already at 110, we know, right? Centroid tells us that this is located at 110. So I will just plug the value here for y, and I will calculate the ratio. Again, the one that is lower value, that is the weakest side. So we call it controlling modulus or controlling section modulus. And I give you last time example that if you have a steel rule like this, you try to bend this one, this is easy to bend, steel rule, right? Because when you calculate, for example, value of I, this will be half, right? This is B, and the thickness of this is height, right? So if let's say B is 10 and thickness is 2, it would be BH cube, right? 2 times 3. You will get this value. But if I try to use this, for example, ruler in this configuration, if I go like this, then you will see that when you try to bend ruler, it will not bend, because when you take half 1 over 12 BH cube, now H value will be higher than the previous case, right? So if it is 2 in term of thickness, maybe this time here, this side is 5. So when you take 1 over 12, B in this case will be 2, and height will be in fact, I should not take this thing. I should take the side here like this. I need to take like this, not like this. So H value will be higher. In this case, what happens? The value of I will be more than this cross section, this value of I, right? So generally, why you cannot bend the steel rule in vertical configuration? Because the value of I is more. The other one is less. That's why it's easy to bend. That's why you pick the controlling section modulus with a lower value, right? So students, here you don't need to use the vertical this side, yeah, the horizontal side like this. You need to use, if there's a steel ruler, let me just erase this part. So if there is a steel ruler like this, One possibility is you consider this side, this thickness, where this is B and this is height. And the other possibility is this vertical configuration, where this small dimension is B and the height is the vertical bigger side. So when you take cube, definitely H value here is more, so it will give you the higher number, right? Maybe if you try to do the calculations, you will see it is maybe around 3 to 4 times higher than this first configuration. That's why this configuration is weak. When you try to bend, apply a moment like this, it will bend. But when you try to put moment here on this configuration, it will be difficult. Are we fine, students, with these two calculations? Any question related to these calculations?
Professor, can you repeat again? Why did we choose the smallest s?
So what I said is that the lower value of this section modulus, it's telling that this is the controlling part, like, because this is where what you can say more bending can happen, right? And I was telling you that, for example, you take the steel rule case. So if I try to bend the steel rule like this, right? Your experience is that you can easily bend the steel rule this way, right? Because we are considering this cross section. So in this cross section, this is B and this is height, right? So when you perform, for example, half 1/12 B H cube, this value is small, right? So you get a lower number. But when I use the same steel ruler like this in vertical configuration, if I try to make it in the vertical configuration, and then if I try to bend, so you have experienced that it will not bend, or it might bend, but not very easily, because this value of H is higher and B is small. So when you do the calculation, 112B H cube, this value is higher. So technically the value of I you are getting is a higher number, right? So this is what it's telling you, that the lower value is more like, it's like more flexible, you can say that, right? Here you are using the value of I same, but because you're considering the outermost fibers, so the values will change. So the lower value has a tendency that this has a controlling influence, right? Because you control through the weaker side, right? You don't design with respect to the stronger side. You always keep in mind the weaker point in the design when you are doing the calculations. Make sense?
Yes, thank you, Professor.
Okay. Then students, the next thing is that we go and we perform the calculations for the stresses. So we are being asked what is the bending stress at point H, and then it is what is the maximum bending stress. These two are the questions in the problem. So if I go back here, where is the centroid? Centroid is located here, right? And point H is located here. So what should be Y in this case? Because I need to execute My over I, right? Can you tell me what is Y here for point H? This is at 110. What should be the value of Y, students? Where is point H located with respect to centroid? Yes.
Professor, is it 40?
So total 175, right? Or if you see this total is 65, we know this thing. 65 minus 25, so remaining should be 40, right? And should it be plus 40 or minus 40? Like, should it be plus Y or minus Y in the formula?
Plus one.
Plus Y, because you remember We said that in our basic formula, we use compressive side as a positive side, right? So if you see, this is on the somewhere here. So this is on the upper side compression. So this value should be positive 40, right? And what other thing is? Other thing is that this moment should be positive or negative. Like if you look at the beam from here, do you see like a positive, like a smiley face or like a sad face? If you are looking at from here, the beam, so the beam curvature is looking like what? The first case, this one, or the second case?
First case,
First case, so moment should be positive or negative.
positive.
That's true. So this should be a positive value provided here in the question already. It's 12 kilonewton meter. Again, you see your initial units are here for the moment kilonewton meter. And you have all the dimensions for I and for Y is in millimeters, right? So the correct way is that you change everything to meter. Okay, so 40 should be divided by 1000, right? To make it meter. This I, what are the units for I? The units are raised to power
Millimeters.
4. Millimeter raised to power 4. So whatever that value is, let's say the value of I is X, how many times I need to divide it by 1000 so that it will get converted into meter. Let's say the value of I is 10. I'm just assuming number. Let's say this is 10 mm raised to power 4. So when I want to convert this 10 into m raised to power 4, what should I do? I need to divide it by 1000, right? Like what I did here. 40 mm, when I divide it by 1000, it will become 0.004 meter, right? What should I do here? How many times I need to divide by 1000? So remember, there are four millimeters, right? So I need to divide this thing by 4 times because there are actually 4 dimensions in millimeter. So each one needs to be converted, right? And then this 12 should be written as 12,000 Newton meter. Okay. Now, students, can you do a quick calculation now for the stress? Use this value of M. Use this value of Y, right? And what was the value of I? This was a big number. Here, this one. Divide this thing 4 times by 1000 so that you get the value of I in meter raised to power 4. And can you tell me what would be the value of stress in this case? And it will come as a megapascal, by the way. So stress is equal to 1200 Newton meter, sorry. Into 0.004 meter. This is Y. And then this needs to be divided by 4 times. So tell me what should be the value, what should be the stress?
Professor, so it's 257
257,
427,
427,
8.6.
8.6. And this came like Newton square meter, which is equal to Pascal, right? So you can see that if you, is it the same number everyone getting, by the way?
Yes, Professor.
Okay. So this is the Newton per square meter or Pascal. And then if I rearrange, if I see there are 3 here and there are 3 here, so I can write it as 2.57 megapascal, right? I can separate these 3 and I can separate these 3, 10 raised to power 6 in fact. So 10 raised to power 6 can be written as a megapascal. Just let me see the values. The answer is 25, not 2.5. So it means that there is something more here, or maybe 1000 is left out somewhere. 10, it's one decimal place is wrong here. Can you double check, students, this number? In fact, okay, I got it. Yes. What was there? It was 40, right? 40 divided by 1000. So technically this is 0.04. The y. So this is not, this is wrong. This is 0.04. Because it was not 4, it was 40. I initially put 4 here. 4 millimeter, in fact. So the one you are not getting correct is technically this one. So once you correct this thing, this will come as 25.7 megapascal. Okay. This initially we put wrong here. This is 0.04. Yes, students, make sense. This calculation is fine.
Yes, Professor.
Can you also do the same calculation for the maximum bending stress? So if I show you, how would you calculate maximum bending stress, students? How would you calculate maximum? Centroid is here, 110. I told you outermost stress is either on this fiber, which is on this extreme, or it would be on the other fiber, which is on the other extreme. How do you know which one is having maximum stress? Do you have more Y here on this side? Or do you have more Y on the other side? Where this Y value is higher, this is the part that will experience the maximum stress. So which one it should be? The fiber on the upper side or on the lower side?
Lower side, Professor.
Lower side, that's true. And in this case, the outermost fiber on the lower side is present as at 110, right? Because we know centroid. It is 110, right? Should Y be positive here or negative?
Negative.
It's negative because now we are going towards the tensile side, right? Tension. So you know that it is minus my over I. So once you plug this y as a negative number, this negative will become plus and your final stress value will be positive, right? When you plug y as a positive number, this answer is negative, which is telling you that it is compression. So the value we just calculated here, this should come with a negative sign, right? Because y is positive in the first case. So this overall value is negative, but this times you will plug the value of y to be negative. So minus minus will give you final answer as a positive, right? So students, it's the same calculation what we just did, right? So you can just simply perform one more calculation for max, which is 1200. It was 12 kilonewton, right? So 12,000. And then Y was basically, it was 110 over 1000. So you can use this. I just simply write it like this to avoid any issue with the calculation, divided by this value. Same thing what you just did. So when you do the calculation, students, you will figure out that the answer is coming as around, I think, 70 megapascal. If you want, you can do this calculation at your own quickly, right? This is a negative value, and you have negative here as well.
Yes,
So your
Professor,
final-
70.8 megapascal.
Yes, which is here. So that is the idea, okay? And that is kind of a walkthrough of calculations. Shape can be anything. Shape can come in many ways. Like I have given you last question, if you remember, the one that I also included in the homework, that it has to be like this. There was a beam that was inverted U-shaped profile. So that if you see all steps are there, right? You can look into that as well. Then I have also another problem that I will leave it for you just to solve this thing at your own, but the steps will remain the same. Here I am dealing with this I-beam, but this I-beam is not symmetric. If it is symmetric, then the centroid will always stay in the middle. So things are easy. But if it's not symmetric, then the centroid will get shifted from the middle, the overall centroid, I mean to say. So here you are dealing with three rectangles. This is, let's say, separate rectangle. This is separate. This is separate. So you need to compute with respect to three areas, right? Initially, you will end up with y1, a1 plus y2, a2 plus y3, a3 divided by the total area a1 plus a2 plus a3. This is the formula that will give you the total centroid, right? Again, you need to benchmark first the reference point. So reference is generally ground in most of the calculations. So you will figure out the centroid like this, then you will go back, you will figure out the the value of I for each one. This is I1, this is I2, this is I3, individual one by using the same formula 1/12 BHQ. And after that, you need to convert all of these I1, I2, I3 with respect to the new centroid. So the total centroid may be somewhere here. You need to figure out the value of D for each one of the areas. And then you need to utilize I total 1 by using I1 plus A D square, parallel axis theorem, right? To shift this AI1 to the actual centroid, the total centroid. Same thing for the second one, same thing for the third area. And then in the end, you will add all of these three components to get the total I, right? Then here you will again do one more calculations with respect to the section modulus for the upper side and the lower side, for example, right? And after this one, you will go for the calculation of same points, different points are there. So point H needs to be calculated. If I show you point H is there, you need to figure out what is the right Y. K is there, and then maybe the outermost fibers for maximum stresses. So the flow remains the same. The steps are the same, only the shape can be different. So please practice this thing at your own. Do all the calculations for this one. The other problem I have given in my previous slide as well, that is also part of homework. So do these practice, students, and I hope that you got the concept. If there is any question, let me know. Is it fine, students? You can do this thing at your own?
Yes.
Okay. Any question from the problem solving part that we did? No questions?
No, Professor.
Okay, that's fine. What I'll do,